Thank you for the introduction, Dr. Rodriguez. As he mentioned, I'm John Vance. I'm working with the Renewable Materials and Bioenergy Research Center at West Virginia University. And today I'm going to discuss an ongoing project we have that is a USDA NEFA funded project called Advancing Forest Logging Residue Harvest and Collection Logistics in the Eastern US. The project is led by our group at West Virginia University in partnership with Virginia Tech, Auburn University, and the University of Maine. So a quick outline of my presentation, I'll introduce our team, the study region that we're working with, our project goals and objectives, the overall framework and supply chain that we're studying, along with introducing a few of our field operations and study sites and some key outcomes and deliverables we're hoping to accomplish with this project. Our team is led by Project Director Dr. Jingsing Wong at West Virginia University, along with co-investigators Dr. Chad Bolding of Virginia Tech, Dr. Tom Gallagher of Auburn University, and Dr. Anil Kija from University of Maine, along with myself as a research associate and approximately 8 graduate students currently working on the project. Our study region is the entire Eastern US, and we've divided this up to focus and expand our efforts into 4 subregions. We delineated these regions and allocated one to each of our partnering universities based on the forest stand types and typical harvesting practices, similarities in each of those 4 subregions. Our overall project goal was to develop and optimize forest logging residue harvest and collection logistics in the Eastern US. We're accomplishing that through 4 key objectives. So our first objective is to investigate the forest logging residue harvest and collection system, production rates, and cost estimates. We're doing that through a series of field time motion studies. Secondly, we want to configure and optimize the logistics of logging residue harvest and collection systems through logistics modeling optimization. Third, we want to quantify the environmental impacts of best management practices for forest residue collection. So we're also on those study sites where we're doing time motion studies. We're analyzing BMP and forming a recommendation for policy implications related to biomass harvesting versus traditional logging. And lastly, we're conducting techno-economic analysis of forest logging residue supply chains and the potential market impacts in those regions. The framework of our task to accomplish this project. First, again, we're working on integrated harvest and collection through time motion studies and field sites. In those, we're collecting production cost data along with fuel consumption and emission data. We're performing BMP checks for the environmental impact assessment and utilizing that data to fuel a life cycle assessment. For logging logistics optimization, we're delineating modeling and optimization of the supply chain for productivity and cost, generating biomass price curves specific to each region and subregion that we're studying, and performing specific case scenarios with sensitivity analysis in those specific field sites and industry partners. The supply chain that we're studying consists of forest logging residue as our primary feedstock. We're studying each type of typical harvesting system in those subregions, including chainsaw, manual felling, mechanized harvesting systems with feller buncher and grapple skidders, along with harvester forwarder systems. Studying the chipping or densification for that logging residue, and then transportation from the field site to pre-processing facilities. One study site that was observed was in Ohio, near the Zanesville and Gnadenhutton, was 2 sites in Ohio. On that site, they were using a Timco feller buncher, along with 2 grapple skidders, feeding a Moorbark 27 RXL chipper. They were producing poultry wood chips on this site. We found that the chipper productivity was approximately 65.8 tons or 1,473 cubic feet per productive machine hour at the chipper, with a delivered productivity to the mill site of approximately 7.7 tons per productive hour. We used our time production data to develop a chipping productivity regression model for estimation of chipper productivity. And we delineated chipping cost at $72 per productive hour at the chipper, or approximately $2 per green ton or $3 per dry metric ton for chipping cost alone. So that's the estimated cost for if we were to integrate chipping into traditional timber harvesting. The total harvest cost, including chipping and the mechanized harvesting, was approximately $8 per green ton or $14 per dry ton, along with a total delivered estimated cost at $10 to $14 per green ton or $18 to $24 per dry ton. A couple of our other sites that are being currently studied or ongoing with our other university partners. So one site handled by our partners at Virginia Tech is in Stony Creek, Virginia. That's a harvest system using 2 rubber-tired feller bunchers, grapple skidders, and a more bark chipper. They're producing wood chips, pulp, and saw timber, so it's an integrated logging and residue collection system. Another operation covered by our partners at the University of Auburn in Bonifay, Florida, where they're using a tiger cat feller buncher and more bark chipper to produce wood chips for pellet production facility. And another operation covered by our partners at Auburn in Gainesville, Florida, where they're performing chipping using 2 bandit chippers, 2 John Deere feller bunchers, and multiple skidders to produce chips for a power generation plant. Along with estimation of productivity and costs for these residue collection sites, we're also performing feedstock characterization for analysis of these residues as a feedstock for bioproducts or potentially biochar or other energy products. Those include analysis we're performing include green moisture, bulk density, piece size distribution of the wood chips, bark content, calorific heating value, and then proximate and ultimate analysis for chemical composition. For the site in Ohio, we collected wood chips of mixed hardwood species. You can see some results, including the green moisture content, bulk density, bark, and heating value in the associated tables. We found moisture content of those green chips at approximately 37.5% moisture content and heating values ranging from 7,700 to 8,800 BTU. For the additional logging residue sites, we are collecting residue species specific and solid pieces for 1 to 5 year post-harvest residue and analyzing the degradation effects for how long it is effective to revisit logged sites for residue collection as a bioproduct feedstock. Some key project outcomes and deliverables we hope to accomplish with this project is to develop production and cost models for forest logging residue collection. We want to examine again those effects of degradation on biomass quality for 1 to 5 years post-harvest for hardwood and softwood residues and specific to each of our 4 subregions. We're going to determine the physical, chemical, and thermal properties of those logging residues by age, class, and region for the effectiveness of that logging residue collection. We want to create a decision-making framework for integrated residue collection and determine the most productive and cost-efficient systems for integrated residue collection. We're working through our modeling to do optimization of the forest residue supply chains and quantify the impacts of feedstock supply and demand, do market surveys to assess the current market situations for forest residues. We're also working with our BMP studies to create a set of guidelines for integrated timber and biomass harvest collection and how those BMP guidelines or recommendations could differ when harvesting biomass is considered a traditional hardwood or roundwood logging. And we want to identify our market uses and business models to increase further utilization of logging residue in the eastern U.S. Thank you, and I'll turn it over to Dr. Rodriguez again for the next presentation.